Organic chemistry is a challenging subject for most students. By the end of Organic Chemistry 2 courses in college, students typically need to learn general aspects of over 100 reactions, and they also need to understand many subtle nuances that can affect the products of those reactions, things like stereochemistry, carbocation rearrangements, and resonance, to name a few. One misguided strategy many students take is to write down all the reactions they need to know on flashcards and then try to memorize each one. This strategy often leaves students frustrated because test questions are never as simple as the reactions that are drawn on the cards. Not only that, flashcards are a poor learning tool for organic chemistry, as a true understanding of the subject does not come from rote memorization. Rather, it comes from a deep understanding of why reactions happen the way that they do. This leads to the question, if memorization is not the key to understanding organic chemistry, what is? Is there a better way to learn how reactions work? The answer, of course, is a resounding yes. And what I'm going to outline in this video is 4 simple steps that will help students make sense of the endless list of facts they are expected to keep track of during their study of organic chemistry. If implemented consistently and completely when students work on problem sets and test questions, it will help them gain a deeper understanding of a complicated and confusing subject, and likely help their grade as well. I call it the Organic Chemistry Reactions problem-solving process, and I'm going to outline the process right here, and then I'm going to walk you through a practice problem showing just how powerful it can be when approaching problems. When considering a reaction, A plus B yields, and you need to figure out what the product is, the first step of the problem-solving process is to identify the functional group or groups on reactant A and make a list of what you know about it. This list can include many things. For example, is the functional group acidic, basic, nucleophilic, or electrophilic? Is it an oxidizing or reducing agent? How is the charge distributed across the functional group? Most importantly, probably, is D, what types of reactions are possible with this functional group? And then, are there any other key facts that are important to know about this group? Once that list is made, you can move on to step 2 of the problem-solving process, which is identify the functional group or groups on reactant B, and again, make a list of what you know about it, using the same A through E as above. Now that we've done that for both of them, we should hypothesize how the functional groups will interact with each other, and then draw the reaction mechanism, if applicable. And usually, the reaction mechanism is very applicable, but sometimes it's not. And then we're going to predict the product or products that occur as a result of that mechanism. Now, a lot of students stop there. They're happy with what they've done, but there is a 4th step here, and this one is just as important, if not more important, than the other steps. And this is to check your answer by considering the following. Look for any resonance in the intermediate. If there's resonance, it's possible that the resonance forms will change the products that you get, or add another product or products. B, carbocation rearrangements. If your intermediate includes a carbocation, is it possible to make a more stable carbocation? If so, it's going to happen. And then C, stereochemistry. Is there a stereogenic center in your product? And what mechanism formed the stereogenic center? This will let you know if you get an inversion of stereochemistry, or if you get 2 answers, for example, a racemic mixture. And the second part of stereochemistry is, did you create a new double bond? If you did, you should always consider cis versus trans isomers, or if it's a more complicated double bond, E versus Z stereochemistry. On this page, I have a reaction. The first step of the problem-solving process is, of course, to recognize or identify the functional group on the first reactant. And what I notice here is that I have an alkyl halide, and it's a 2nd-degree alkyl halide. So I have a 2nd-degree alkyl halide. Now I know a couple of things. The bromine here is a lot more electronegative than the carbon. So the bromine is partially negative, which means this carbon, the alpha carbon here, is partially positive. I also know that bromine is a good leaving group. In addition, 2nd-degree alkyl halides can undergo a lot of different reactions. They can undergo Sn2, E2, E1, and Sn1 reactions. The second step of the problem-solving process says that I should look at the other reactant now. I have CH3OH, and what is this? This is an alcohol. what do I know about alcohols? Well, alcohols, they have an OH group, and the OH group has lone pairs on the oxygen. That means alcohols can serve as both weak nucleophiles and weak bases. If it acts as a nucleophile, then it is going to do Sn1 reactions. And if it acts as a base, it can do E1 reactions. So now we can look for overlap between what types of reactions these two reactants do. And we can see we have an overlap between E1 and Sn1. So that means we're going to do both reactions. So now I've predicted or hypothesized what type of reactions it's going to undergo. So let's draw a mechanism. So for Sn1 and E1, the first step in the mechanism is exactly the same. The leaving group is going to leave. So we're going to draw an arrow here to indicate the leaving group is going to leave. That's going to leave me with a second-degree carbocation right here. Now, I'm going to jump a little bit ahead here, just because I don't want to waste time showing you the wrong way to do this problem. Step 4 of the problem-solving process says to check your work, essentially. And what we have here is a carbocation, and it's a second-degree carbocation. Is it possible to make this a third-degree carbocation, making it more stable? And absolutely. So what we have here, we have a hydrogen bonded to this carbon. And what we can do is we can do a 1,2 hydride shift. So this hydrogen is simply going to move over here. We're going to call this a 1,2 shift. And what that's going to do, it's going to move that hydrogen over to the other side. I'm not going to draw the hydrogen in, but we know it happened based on the mechanism. And that's going to move my carbocation over here to the third-degree position. So now I have a third-degree carbocation, which is a lot more stable than a second-degree carbocation. And anytime you can make a more stable carbocation, you're going to do it if you can do it via a 1,2 hydride or a 1,2 methyl shift. So the first step of my reaction mechanism is simply this, the creation of the carbocation. Now I have two different pathways that I can undergo. I can undergo the Sn1 pathway, or I can undergo the E1 pathway. So I'm going to move this new carbocation down here. So let me draw that line down here, and I'm going to move this down. And here, let's draw the Sn1 pathway first. One thing that I always like to say is organic chemistry is the science of drawing arrows from negative charges to positive charges. So right here for the Sn1 reaction, I have the lone pair, which serves as my negative charge, and I have a carbocation, which is my positive charge. So all that's going to happen here is I draw that arrow, and that represents the formation of a new bond and the removal of that carbocation. So I have my O, it's still bonded to the H, and it's bonded to a CH3. So I have that group there, and I still have the rest of the molecule as is. Of course, that puts a positive 1 formal charge there, so what's going to happen is another molecule, probably another CH3OH, is going to come in, and we're just going to get a proton transfer. And that will simply give me a neutral oxygen. And that here is a methyl group, not a negative charge. So now I have to check my work. So when I go to step 4 of the problem-solving process, I have to consider things like stereochemistry. So now I check for stereochemistry. And what did I have? Well, I had a stereogenic center, or I created a stereogenic center. I went from trigonal planar, which is the carbocation. Now I have a stereogenic center. I have 4 unique bonds to this carbon. And because I have a new stereogenic center, I have to consider what the mechanism was. I had a carbocation. A carbocation on a carbon indicates that that central carbon was trigonal planar, which means that it's flat. So we have a 50% probability that when we attack with a nucleophile, we're going to attack from the top side, and a 50% probability that we're going to attack from the bottom side. So that means we can either do a front side or a back side attack. That means I should have 2 different products. So I'm going to draw the same product. But now on one of them, I'm going to assign one of them a wedge, and another a dash, And then on the other product, I'm going to have the other configuration. So I'm simply going to put the thing that I had on a wedge on a dash now, and the thing that I had on a dash, I'm going to put that on a wedge. And there we go. I have my Sn1 reaction, and I have my two products. Next, I'm going to consider my E1 pathway. So I start the same way. I have that carbocation that I formed above. And for my E1 pathway, I know that I need to label my alpha carbons. So my alpha carbon is where the carbocation is. And then my beta carbons. My beta carbons are carbons that are directly bonded to the alpha carbon. So I have 3 beta carbons. And I'm looking for beta hydrogens. So I have on this top left beta carbon, there's 2 hydrogens. I only need to draw one of them. On the bottom left one, there's 3. Again, I only need to draw one. And on the one on the right, I have 2, but again, I only need to draw one of them. This tells me that I'm probably going to have 3 different E1 reactions that are going to occur, where I can remove any of those beta hydrogens. So if I remove the top one, I draw an arrow from my lone pair to my hydrogen, the carbon-hydrogen bond breaks, and those electrons go to form a double bond. So then I get this as one of my products. Of course, I could have grabbed this hydrogen or this hydrogen as well, in which case I would have gotten 2 more products. So I'm not going to draw the mechanism for both of those, but I will just draw those products. So there we go. I have those 3 products. However, I'm not done, because step 4 indicates that I should check my work. And what did I do? I formed a double bond. Several different double bonds, actually. So what should I do? I should check for E or Z isomers. So anytime I form a double bond, it's possible that because I had a single bond before with that carbocation, it's possible that I have a different rotation around those single bonds where the double bond is formed. So that means for this top product here, it is possible that I have another configuration. That is going to be both the E and Z isomers. Then for the bottom left one, I can also have a different configuration. And again, there's my E and Z isomers. So you can see I actually have 5 different E1 products, and I had 2 different Sn1 products. And if you go through the entire problem-solving process, you won't miss, hopefully, any of those products. So there you have it. There is the organic chemistry problem-solving process, and you've seen an example of applying this in a situation where you might not have gotten all of the products otherwise.